Okay, and welcome to the video on equilibrium revision. So equilibrium refers to a state in which the reaction has reached a state in which the rate of the forward and reverse reaction are equal. That means that the forward and the reverse reaction rate are the same. If we do a simple example of A producing B, this means that the reaction is reversible, which means that it can reach an equilibrium if you let it go. If we plot rate versus time, and if I start with only A, I could have started with only B, but I'll start with only A. It means that at first, you only have a forward reaction. Okay, so the forward reaction starts off with a high rate. Then what happens is you use some of the A to produce B, and the concentration of A decreases over time, okay? And therefore, according to rates, if the concentration decreases, the rate of the forward reaction decreases over time too. Okay, so you'll get something like this. The forward reaction will decrease over time until it reaches a constant value. On the other hand, we have the reverse reaction, which starts off at 0 if we start off with only A, because there's no B to produce A. But as we start producing B, the concentration of B increases over time, which means that the rate of the reverse increases, which means that we get something like this, and then they will be equal at equilibrium. So this is the point at which equilibrium is reached. Oops. So the concentrations of A and B are constant at this point. Constant at equilibrium, but not necessarily equal. The temperature remains constant because the rate of the exothermic equals the rate of the endothermic, so the net release and the net absorption of energy is equal as well. The pressure will be constant if you've got, gases, because again, the concentration will be constant. Okay, so that's a little bit of that theory. The next amount of theory is about the equilibrium law. Equilibrium law, is found experimentally. It was found that if you have a reaction, for example, N2 plus H2 produces NH3, and then we balance, so we'll pop a 2 there and a 3 there. It was found that at equilibrium, the concentration of the products to the power of their coefficient divided by the concentration of the reactants to the power of their coefficient is equal at equilibrium. Okay, so is constant at equilibrium. So constant applies at equilibrium. But it's different depending on temperature. So temperature is the only factor which changes K. All right, so even if we start off with different concentrations, they will change their concentrations by either favouring the forward or reverse reaction until the new equilibrium is reached, which will equal K again. This is a really good little system here because it allows us to grab concentrations at any point, conc at any point, and calculate Q, which is the concentration fraction. It is calculated at any stage in the reaction, but if Q is not equal to K, we will get a shift, either forward or reverse. If Q is less than K, what that means is that we have, so if Q is less, remember it's products divided by reactants. It means that we have less products than should be at equilibrium. So we'll get a net forward reaction or shift to the right. If Q is greater than K, we have more products than should be at equilibrium. So we'll get a net reverse reaction or shift to the left. And the system will shift until we reach new equilibrium, until Q equals K again and equilibrium is restored. So that's saying that Q originally equaled K. So if Q originally equaled K, let's just say at T equals 1, okay, and then we add products, what happens is Q will be greater than K, and then you'll get a shift to the left, okay, and then that will act to reduce Q, and let's say at T equals 2, these are arbitrary times, Q equals K again. This is a state when you are shifting a system out of equilibrium. So you're shifting a system out of equilibrium. You're adding a stress, so it partially opposes this change. But let's just say that you add only products. If you add only products, Q will still be greater than K, and you'll still get favoring of the reverse reaction so that Q can equal K. You just wouldn't say partially opposing the change in this case because the system wasn't at equilibrium to begin with. And that brings us to Le Chatelier's principle. Le Chatelier's principle is reserved for when we have a system at equilibrium. So it's when Q equals K. So Le Chatelier's principle states that when an equilibrium system is subjected to a change which shifts it out of equilibrium, which results in it being thrown out of equilibrium, the system shifts to partially oppose the change so that equilibrium can be restored. In terms of Q versus K, when an equilibrium system, so that's a system in which Q equals K. So when an equilibrium system is subjected to a change which results in it being thrown out of equilibrium, in other words, Q does not equal K anymore, the system shifts to partially oppose the change, okay, so that Q can equal K again. And there are ways that you can do this. So the changes you can make. There are a number of changes. One is a change in pressure by a change in volume. And what that will mean is that Q does not equal K in some, but not all cases. So I'll show you a case where it doesn't. When there are equal number of particles on both sides, like for example here, okay, if I, let's say, reduce the volume, this will increase the pressure, it will increase the concentration of all of my reactants and products. But because there are an equal number of reactants and product particles, so there are 2 mole on the left-hand side and 2 mole on the right-hand side, the system is not shifted out of equilibrium. And I can show that with Q as well. Let's say that at 25 degrees Celsius, this is all fake here, K equals, let's say that the concentration of HI is 2, so 2 squared divided by 2 times 2, just to make it really easy, 4 divided by 4 equals 1. Let's halve the volume. So we'll keep it at 25 degrees Celsius and we'll halve the volume, okay? What that will do, now notice that I'm writing Q because I'm not sure if it's at equilibrium, so I should write Q. If I halve the volume, what happens is I double the concentration. And what that does is that turns that 2 into a 4, and that turns the other 2's into 4 as well. And we actually get 16 over 16, which equals 1. As you can see, Q still equals K. This is not the case if I have a different number of particles on each side. Like we'll take our ammonia example. Again, oops, NH3, and we've got 3 there. Okay, so let's say that let's just give them all 2 as well, just to make it nice and easy. So 2 squared divided by 2 to the power of 3 times 2 equals 8. Okay, so equals 4 divided by 8 times 2 equals 4 over 16 equals 0.25. And if we want to give these units, it didn't have any units on the other one, but you just go, because the square brackets have the units m, so it's m squared divided by m to the power of 3 times m equals m squared divided by m to the power of 4 equals m to the negative 2. Now let's say that we halve the volume, which has the same effect of doubling the concentration. Okay, and what we do there is we work out Q. So 4 squared divided by 4 to the power of 3 times 4 equals, and I'll just do a quick calculation, 64 times 4, 0.0625 m to the negative 2. What we've done here when we've halved the volume is we have made it so that Q is less than K, which means that we get a shift to the right to increase Q and allow Q to equal K again. If you explain this in terms of Le Chatelier's principle, you would say that when we halve the volume, concentration is doubled, or pressure, you could say, pressure is doubled, to partially oppose the increase in pressure, the system shifts to the right to favor the side of the reaction which produces less mole or less moles. Okay, so that's the right hand side. So it works with Q and with K. Another time that you won't shift a system out of equilibrium is if you add an inert gas, because that's not going to change Q, the concentration fraction. Okay, another way you can shift a system out of equilibrium is by adding reactants or products. And let's just go back to the ammonia example. Let's say we add N2. The way you would explain this in terms of Le Chatelier's principle is that if we add N2 to partially oppose the addition of N2, the system reduces N2 by favouring the forward reaction. You can also see that Q in this case would be momentarily less than K because we've added products, which is in the bottom of the reaction, the equation. So again, you'll get a net forward reaction to increase Q. Okay, another way you can do it is by adding reactants or products, temperature. Now in this case, temperature is a little bit different because you'll see that there'll be no immediate effects on Q. So Q has not changed, but temperature changes K. So let's do a fake example. Let's say delta H is positive. What that means is that this is an endothermic reaction, and you can think about it as energy is on the reactant side. Well, it's absorbing energy. There's a net absorption. So the way you can explain this in terms of Le Chatelier's, an increase in temp will be partially opposed by the system by favouring the forward energy absorbing endothermic reaction. So increase in temperature increases K for endo reactions for this reason. If you have an exo reaction, you have the opposite. So let's just say D plus E produces F. And then we'll say delta H is negative. You can think about it like energy on that side. And you could say an increase in temperature favors the reverse endothermic reaction. So increase in temperature to partially oppose the increase in temperature. I'll just write it out like increase rather than arrows. To partially oppose the increase in temperature, the system shifts to favor the energy absorbing reverse endo reaction. In other words, shift to the left. So for exo reactions, when you increase temperature, you actually decrease K. You still make it that Q doesn't equal K anymore, but Q equals the old K at the old temperature, if it was at equilibrium, but Q does not equal the new K at the new temperature. So the final way in which we can shift a system out of equilibrium is through a dilution. So this has the same explanation pretty much as a volume change. When you're diluting, you are decreasing the concentration of dissolved particles. So for example, let's say you've got A aqueous plus B aqueous produces C aqueous. You have 2 mole on the left-hand side and 1 mole on the right-hand side. If you dilute, you could say to partially oppose the reduction of reduction in concentration of dissolved particles, the system shifts to the left, to produce more dissolved particles. It favors the side of the reaction which has more moles, which produces more moles. Okay, so that's pretty much equilibrium in a nutshell. And now we are going to do some questions. Okay, so let's start answering some questions. Okay, write a balanced equation for this reaction. Well, this is pretty easy because you're just going backwards. A few things you need to remember. Products over reactants. So the products are NO. You've got to put the state, says that all species are gases. And it's to the power of their coefficient plus Cl2 gas. Double arrow, 2NOCl gas. Okay, calculate the value of K. All right, so first of all, the reverse reaction would be NOCl 2 over NO squared Cl2. 2. Okay? Mathematically, to turn this into this, you would have to do 1 over 1.6 times 10 to the negative 5 equals 6.3 times 10 to the negative 4. And if we want to have a look at what the units would be, m squared divided by m squared times m. M squared divided by m to the power of 3 is m to the minus 1. Okay, just while that's kind of fresh in our minds, I'll remind you of a couple of other things. So number 1 is that if you double the coefficients, k new equals k old squared. If you halve the coefficients, k new equals k old to the power of a half, or the square root. Let's move on. C. Okay, so we put some in an empty container. So we're starting off with only NaCl, which is the reactants according to that equation. The reaction is allowed to reach equilibrium, and we have 0.0156 mole of Cl2. So calculate the concentration. So that's pretty easy. Concentration of Cl2 equals N over V equals 0.0156 over 1.5 equals 0.0104. It's asking us next to calculate the concentration of NO, which is the other product. So we know that we started off with only reactant. That means that these two will be produced at their mole ratios. So to produce 1 mole of Cl2, we need to produce 2 mole of NO. Because we produce 0.0156 mole of Cl2, the moles of NO at equilibrium will be 2 times 0.0156 equals 0.0320 mole. And then in concentration, what did I do? 312 mole. And then in concentration, it will be concentration of NO equals moles over volume equals 0.0312 divided by 1.5, 0.0208 mole per litre. Now, determine the concentration of NaCl. Let's use the equilibrium expression. So, let's fill in the gaps. K is 1.6 times 10 to the negative 5. NO's concentration is 0.0208 squared times Cl2's concentration divided by NaCl squared. So 1.6 times 10 to the negative 5. I'm going to multiply it by NaCl squared so that I can bring that onto that side. Equals, let's just calculate this, squared times 0.0104 equals 4.50 times 10 to the negative 6. We then divide that by 1.6 times 10 to the negative 5. Oops, and we get 0.281. And that's NOCl to the power of 2. So we take the square root of both sides, which eliminates the squared, and we get 0.530. Okay, next, determine the mole, in mole, the amount of NOCl initially added. So initially added will depend on how much we have at equilibrium, okay, and also the change. So how much has reacted? So let's do a little equation. NOCl initial equals NOCl at equilibrium plus NOCl reacted. How do we know how much is reacted? Well, it will be 2 times the Cl, or it will be equivalent to the NO mole. Because to make 2 mole of NO, I needed to use 2 mole of NOCl. So I can just pluck that many mole. That's how much will have reacted. So 0.0312. So let's add that to the equilibrium mole. The equilibrium mole will be N equals C times V, 0.530 times 1.5. 0.795. I'm keeping these all in my calculator, and I can actually go all the way back and add it to the 312. 0.827 mole. And let's just double check. Excellent. All right, next question. Write an equilibrium expression. That's pretty easy. So K equals BR2, you don't pop the states in, times NO squared over NOBR2 squared. That's pretty easy. Three mole of NOBR2 was added to a 4-litre reaction vessel. Once equilibrium was reached, 0.805 mole of Br2 was present in the mixture. Calculate the equilibrium constant. So if it's got an initial and also an equilibrium one, I'm thinking an ice table. That's kind of what tells you. So the way you set up an ice table, I'll just zoom in. Excellent. So the way you set up an ice table is you write out the reaction again, which is 2NOBr, just to keep your coefficients there. 2NO plus Br2. Suppose you don't need those states there. But anyway, we write ice, which is initial, change, and equilibrium. So this is initial moles, change in moles, equilibrium moles, and equilibrium concentration. So then we can actually go straight to K. Might rule it just to make it a little bit neater. Yeah. All right, we're ready to go. Now let's plug in what we have. 3 mole of NOBr. So that's our initial. Was added to a reaction vessel. That implies that we have none of the other two. Once equilibrium is reached, we have 0.805 mole. Okay. Now the change is where you're going to be doing the stoichiometry, because that's where the reaction is occurring. So that's where we do our mole ratios. So let's have a look. 0.805 okay. This is, I always do the actual change because if the products go up, the reactants need to go down, okay? Because it means that you've used up some reactants. So bromine has gone up by 0.805. That means NO has gone up by twice that amount, so 1.61. So its equilibrium mole will be 1.61. That means NOBr2 has gone down by 1.61. And that means its equilibrium moles will be 1.39. Okay. Now, if I want to go to concentration, I have to go concentration equals moles over volume. So I'll have to be dividing all of these by 4. So brings this to 0.3475. 0.4025 and 0.2013. Okay, now these are actually concentrations, not mole anymore. So we can put them straight into K. K equals 0.2013 times 0.4025 squared divided by 0.3475 squared. Okay, now just keep it all in your calculator. So multiply that by that squared. Divide that by that squared. And we get 0.270. And the units are M. All right, next question. In a second reaction mixture, also 4 litres, the concentration of the gases were found to be that and that. Calculate the concentration of NO. All right, so we're assuming that it's at equilibrium. Yeah, I suppose so. It's the only thing we can do. Now that we know K, we can put 0.270 as K, and it equals NO squared, which we don't have and we are trying to calculate. But we multiply that by Br2, which is 0.0405, and we divide that by NOBr, which is squared. All right, and then we times it by 0.057 squared, divide it by 0.0405. Okay, so NO squared equals 1.71. We'll take the square root of both sides. Okay, equals 1.3. Let's just check. 1.31 M. Okay, now final one. Would the equilibrium yield be favoured by a low or high temperature? Use Le Chatelier's principle. All right, so let's have a look if it's exo or endothermic. So delta H is less than 0, which means that delta H is negative, which means that it's exo, which means that there's energy on the product side. if we decrease the temperature, it will shift to the right, favouring the exothermic reaction to produce more energy. Okay, so first of all, we got 3 marks to play around with. So we will say that it's favoured. One of the marks should be favoured by a low temperature, hopefully. So low temp. Because the reaction is exothermic, to partially oppose a reduction in temperature, the system shifts to favour the forward energy producing or net energy producing exothermic reaction. And let's just double check. So they say a low temperature, the reaction is exothermic, so the yield will be favoured by low temperatures. Le Chatelier's principle states that when an equilibrium system is subjected to a change, it will adjust to partially oppose. In this case, it means shifting to the exothermic to increase the temperature. Exothermic, we said that, and valid references. Cool. All right, so question 4, I will skip. You can do it by yourself. Let's just check. Cool. So question 5. All right, let's just focus that one in. Cool. So what change was applied at time T2? So you can see that there's no sharp increases or decreases in concentration. So when there's only a gradual change, it means that it was temperature. Think about the other ones. If you decrease concentration, if you decrease volume, you'll increase concentration, so you'll get spikes. If you dilute, well, for an aqueous one, you'll get drops. If you add reactant or product, you will get a sharp increase. Like for example here, we've added something. So gradual is temp. Now, which side has it gone? It's actually gone to the reverse reaction. And it's gone to the reverse reaction, and the reverse reaction is exo. So it's favoured the exothermic reaction, which means that what we have done is we've decreased temp. So explanation, a decrease in temp will favour the exothermic reverse reaction to increase temp. Let's just check that according to Le Chatelier's principle. Temperature decreased. Reaction is endothermic. As temperature decreases, K decreases, or reaction moves backwards to produce more. So you could also explain it in terms of endo. Question 4. Consider the graph. Let's have a look. So we've got a few things happening here. First of all, K equals Q here. It's at equilibrium. Second of all, we have an addition. But what one do we have an addition of? Well, let's have a look. So what you can tell is by the shift. So the shift occurs between here and here. And to connect this to the ice table, it's change. And this is where your mole ratios are occurring. Because if we're increasing one, we need to decrease the other by the mole ratios specified by the equation. So the fact that this one, it looks like a 1:2 ratio here, means that we're shifting to produce more of the NO2, which means that we've probably added N2O4. Now let's play this story in our head. So we add N2O4, it then shifts backwards to reduce N2O4, but it only partially opposes the change. N2O4 concentration is still higher than the original. So we've added N2O4. So it's either C or D. Okay. Remember that this reaction, delta H, has to be... okay, we don't even need that. But anyway, delta H is negative because it's positive here. I don't think that these two questions are related though. Because if you have a look, there is only temperature for one of them. And you can see here that there's no, at change 2 at 10 minutes, there's no sharp increase or decrease, which means that it's actually a temperature change. So it has to be D. But let's check with, because we actually know that it's exothermic. If we've decreased temperature, it shifts to the right-hand side, which means that we're producing more N2O4, which is this line. So it makes sense either way. And let's just double check that we got the answer. And it is in fact D. Okay, question 9 and 10. Put those in focused. All right, nitrogen gas and oxygen gas can react according to this equation. 3 different flasks. The concentration in mole per litre of the components is shown below. Which of the flasks is at a different temperature? So what I would do is just calculate Q for all of them. But it says, at equilibrium. So calculate K for all of them. K only changes with a change in temperature. So for the first one, K equals 0.15 squared divided by 0.3 squared times Okay, so for X, K equals 0.625. For Y, K equals 0.625. And for Z, K equals 1.61. So what that means is Z must be at a different temperature. All right, question 10. Once equilibrium is reached, 0.6 mole of N2O4, N2O remains. Let's do an ice table because it tells us the initial and then it tells us an equilibrium one. So it's an easy way to sort it out. So write out our reaction. Okay, ice, E, moles, 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 concentration. All right, could rule it, but it'll be okay. All right, so 1 mole of N2O. Now we're starting with product. Placed in an empty container. Once equilibrium is reached, we have 0.6 mole. So we have 0.6 mole. That means we decreased by 0.4. If we go by the mole ratios, this would have to go up by 0.2, half that. And this one would have to go up by 0.4, which means that this would need to be 0.2 at equilibrium, and this would need to be 0.4 at equilibrium. And concentration equals moles over volume. So if I divide that by the volume being 2, I get 0.2 and 0.1. So oxygen has to be 0.1 and nitrogen has to be 0.2, therefore giving us A. All right. Now, question 11. Okay. So I will restructure this. There we go. All right. So the above reaction, is allowed to reach equilibrium. The volume is then reduced. Complete the following concentration times graph. Okay, so if the volume is reduced, the concentration is increased. So the concentration of all of them will go up, but by different amounts. So the amount at which it goes up depends on not its mole ratio, because that's only change, but how much it starts off at. I'll explain this quite using an easy example. Let's say that the volume is halved. That means the concentration is doubled. And let's say that N2 starts at 3, it would have to go to 6. And let's say that H2 starts at 2, it would have to go to 4, because that's what double is. N2 goes up by 3, H2 only goes up by 2, and you can see it's nothing to do with the mole ratios. So let's just show that, even we don't have much more information. So N2 would go up the most. Let's do it all the way up to the top. H2 would be middle, and NH3 would be the least. So the volume is reduced. That means the pressure increases. It shifts to the side with less particles, which would be the product side, because there's 2 on this side and 4 on that side. So it shifts to make more NH3. Let's just do NH3 going up to there. And let's say that it reaches new equilibrium here. So we go petering off here. Yeah. H2, let's just connect these. Okay, now NH3 changes by 2. H2 needs to go down by a factor of 3, or by a mole ratio of 3. Very hard to show, but show that it never reaches the initial, and it needs to reach equilibrium at the same time. Now, to just show VCAR to make it a little bit easier on yourself, you can just do a 3 there. And N2 needs to go down, but just by 1. Also reaches equilibrium at the same point. So to show that they reach equilibrium at the same point, you could just go here, new equilibrium reached, or equilibrium reached. And you could have it leveling off here. And then we go like so. And we just have a 1 here. And we just write here that these are mole ratios. You could go X, X, and X, because you don't actually know the change. Now let's have a look at the answer and compare it. Needs to be the highest, never reaches the original. To show that it never reaches the original, you could actually, in fact, do a dotted line there, showing that it never reaches the original. Okay, because it's only partially opposes the change. All right. Prepare a rate versus time graph for the forward and reverse reaction to represent the rates at equilibrium and for the change. Okay. So I'm just going to get a different piece of paper for that because I will not fit it there. So let's just start ruling. Okay. And let's go rate and time. Okay, so originally the rates were equal for the forward and reverse. So we'd just have two lines superimposed. Then when we have the increase in pressure, according to rates, they would both spike up. Okay. But what would happen is they wouldn't spike up by the same degree. And you can kind of use the next part to help you out with that. So following the change, or actually the change, we have an increase in pressure. The system shifts to the right, which means that reactant concentration decreases over time, which means that forward rate decreases over time. So the forward would increase the most, and then you would have it petering out when it reaches the new equilibrium. Let's say that's there. Okay. Let's say that the new equilibrium is reached about there. The reverse one, let's say it increases to that point, and then the new equilibrium is reached there. Okay, so let's write reverse, forward. Okay, and what you can do is use a highlighter possibly. You could go forward. Okay, and actually they're superimposed here, they're superimposed. Okay, and then you could go reverse, superimposed, bit here. That's where we've got the reverse going up to. And the reverse increases over time because you're getting more products over time. Okay. So here we go. Net forward reaction means that more products obtained per time, meaning that the rate of the reverse reaction increases over time. C. Explain in terms of Le Chatelier's principle the effect on the yield of NH3 when the volume is reduced. Well, I'm not going to really go through that because it's a bit easier than the other questions. But decreasing the volume increases the overall pressure. System moves to partially compensate and decrease pressure by favouring the side with fewer particles. The forward reaction is favoured. So you might want to just have this as a little bit of a guide. You state the change. So decreasing the volume increases the overall pressure. The change is the increase in pressure. You might want to say relate it to the reaction. So the system moves to partially compensate and decrease the pressure. Favouring the side with fewer moles or particles, so that's related to the reaction. And then state the shift. Forward reaction is favoured, and why? It doesn't have to be in this order. System moves to partially compensate and decrease the pressure. So that's a good little guide there. You might want to write this down. Explain in terms of concentration fraction. Okay, so we'll do that one. So in terms of the concentration fraction, well, let's just use common sense. If we are shifting to the right, it must mean that Q is less than K. So to increase Q, shift to the right so that Q can equal K again. So decreasing volume causes the concentration fraction to decrease. So decreasing volume causes concentration fraction to decrease. To return to equilibrium, the concentration fraction must increase, and so forward reaction is favoured. All right, so you can do that one on your own. Let's move to the next question. I thought that this one was quite easy because you can just get it from the graph. Write the equation of the reaction and calculate the volume. Yeah, that's pretty easy. I would say we'll go through part C, which is a little tougher. Okay. Oh, yep. So here it's saying, it's asking, how would the addition of a small amount of hydrochloric acid? The reason I want to go through this is because hydrochloric acid doesn't look like it's in the reaction, but let's relate it to the equation. So we'll state the change. We'll try and follow this guy. Where is it? Oh, oops, it's actually here. We'll try to follow this guide. Okay. State the change. So the change is, how would the addition of a small amount? Okay. Adding HCl, or adding, HCl aqueous. Remember, HCl gas is called hydrogen chloride. Hydrochloric acid is aqueous HCl. So adding HCl aqueous causes, and related to the reaction, the concentration of OH minus to decrease because it reacts with OH minus. The system partially opposes the reduction in concentration of hydroxide by shifting to the right to produce more hydroxide. And let's check the actual answer. Okay, quite small, so I might zoom in a little bit more. Okay. Oh, hang on. Did we answer the question? Gosh, this is bad of me. How would the addition of a small amount affect the concentration of ascorbic acid? Ascorbic acid is the product. Therefore, answer the question, this would increase the concentration of sorbic acid. All right, let's have a look now. The concentration of sorbic acid would increase. Good, we've got that. Because the added HCl reacts with hydroxide or reduces the concentration of hydroxide, thus causing the reaction to shift to the right to partially oppose the change. So, yeah, we pretty much had everything. The concentration of ascorbic acid would increase, we got that, because HCl reacts with hydroxide or causes it to decrease, which we said. Therefore, it shifts to the right, to partially oppose that change. And that's pretty much everything.